Imagine checking your phone tomorrow morning. There's a new message, just 6 words. Do not send the transmission. That's it. No explanation, no name, no context. At first you'd assume it's a prank, spam, a mistake. Then you notice something strange. The message was sent tomorrow, not yesterday, not today, tomorrow. Somehow, a reply has arrived before the conversation even happened. Pause. At first, that sounds impossible. Then it happens again. Scientists begin reporting impossible results. Experiments produce answers before they're performed. Messages arrive before they're sent. Effects appear before their causes. For a while, nobody understands what's happening. Then, a terrifying possibility emerges. Reality itself is breaking. Not because of a black hole, not because of a war, not because the universe is ending, but because humanity has finally achieved something it was never supposed to achieve. We moved faster than light. For generations, people dreamed of this moment, the end of distance, the beginning of interstellar civilization, a future where the stars are finally within reach. It sounds like the greatest breakthrough in human history, but according to modern physics, it could be the worst. Because the speed of light is not just the speed of light, it's the speed at which information moves through the universe, the speed at which causes create effects, the speed that keeps reality logically consistent. And the moment you cross that line, everything begins to fall apart. Time loses meaning. The future starts influencing the past. Paradoxes stop being thought experiments. They become real, which raises a disturbing question. What if the speed of light was never a barrier? What if it was a warning? Because the deeper physicists investigated this mysterious limit, the stranger the story became. The universe doesn't merely prevent anything from moving faster than light, it fights back. Mass increases, time slows down, space itself begins to distort. It's almost as if reality is defending something, protecting something, as if there is an invisible wall built into the fabric of existence. And if that wall ever falls, everything falls with it. For more than a century, scientists have agreed on one thing: nothing can travel faster than light. Not a spaceship, not a signal, not even information itself. But very few people ever ask the obvious question: why? Why does this limit exist at all? Why is there a maximum speed? If the universe is billions of light years across, why would nature impose a speed limit in the first place? At first, the answer seems simple. Maybe it's just a technological problem. After all, airplanes were once impossible, so were rockets, so were computers. Every generation has mistaken a technical challenge for a fundamental limit. Maybe faster than light travel is simply another challenge waiting to be solved. But the deeper physicists investigated, the stranger the picture became, because they discovered something unexpected. The speed of light isn't just the speed of light, it's woven into space itself, into time itself, into the very structure of cause and effect. And every attempt to break that limit leads to the same conclusion. The universe doesn't merely forbid faster than light travel, it depends on that prohibition. Remove it, and something far more important than transportation begins to collapse: reality itself. To understand why, we have to go back to a time when humanity wasn't even sure light had a speed at all. The first crack in the mystery. For most of human history, nobody questioned it. Light seemed instantaneous. You light a torch, and the room illuminates. You open your eyes, and the world is already there. No waiting, no delay, no sign that light needs time to travel. To ancient civilizations, the idea that light had a speed sounded almost absurd. Speed was something horses had, arrows had, rivers had. But light simply appeared. For thousands of years, that explanation was good enough. Then a few people started asking dangerous questions. What if the obvious answer was wrong? One of those people was Galileo Galilei. And that's where the story really begins. Galileo's question sounds simple today. How fast does light travel? But in the early 1600s, it was almost impossible to answer. There were no lasers, no electronics, no precision instruments, no atomic clocks, just human eyes, human reaction times, and a universe that wasn't eager to reveal its secrets. Still, Galileo tried. His experiment was elegant, almost absurdly simple. 2 observers stood on distant hilltops. Each carried a lantern covered by a shutter. Galileo would uncover his lantern. The second observer would uncover theirs the moment they saw the signal. If light traveled slowly enough, the delay could be measured. At least that was the plan. The experiment failed. Every time, no measurable delay, no visible travel time, nothing. Most people would have considered that the end of the story. Galileo didn't. Instead, he reached a remarkable conclusion. The problem wasn't that light traveled instantly. The problem was that light was simply too fast, far too fast for the technology of his era. It was a small insight, but it changed everything, because for the first time, someone had transformed light from a philosophical mystery into a scientific problem. The question was no longer, does light have a speed? The question became, how large is that speed? For decades, nobody could answer. Then the answer arrived from somewhere completely unexpected. Not from a laboratory, not from Earth, but from a giant planet orbiting the Sun hundreds of millions of miles away. Jupiter, the clockwork moon. In 1676, a Danish astronomer named Ole Rømer was studying one of Jupiter's moons, a moon called Io. At first glance, there was nothing special about it. Io simply orbited Jupiter, again and again and again, like a cosmic clock. Every orbit produced a predictable eclipse. The moon disappeared behind Jupiter, then emerged again. The timing was so regular that astronomers could predict it with remarkable accuracy, until something strange happened. The predictions started failing, not dramatically, just a little. Sometimes Io appeared earlier than expected, sometimes later, a few minutes here, a few minutes there, nothing that looked revolutionary. Most astronomers ignored it. Rømer didn't. He kept watching, month after month, year after year, and eventually he noticed a pattern. The delays weren't random. They depended on where Earth was in its orbit. When Earth moved closer to Jupiter, the eclipses arrived early. When Earth moved farther away, they arrived late. At first, that observation made no sense. The moon wasn't changing. Its orbit was stable. Jupiter wasn't changing. The predictions weren't changing. So what was? Then Rømer had a realization that would transform humanity's understanding of the universe. The delay wasn't happening at Jupiter. The delay was happening in the space between Jupiter and Earth. Light itself was taking time to travel. For the first time in history, someone had discovered that light was not instantaneous. It moved, and that movement had a finite speed. The exact number wasn't perfect. Modern measurements would come later, but the conclusion was undeniable. Light traveled incredibly fast, yet not infinitely fast, and suddenly the universe became much larger than anyone had imagined. Because if light takes time to travel, then every observation comes with a delay. The sun we see in the sky is not the sun as it exists right now. It's the sun from 8 minutes ago. The nearest star, you're seeing it years in the past. The Andromeda galaxy, more than 2 million years in the past. Without realizing it, humanity had discovered something extraordinary. Looking deeper into space means looking deeper into time. The night sky isn't a snapshot of the present. It's a collection of ancient messages. Every star is sending information across enormous distances. Every beam of light is carrying a piece of history. Some of the stars you see tonight may no longer exist. Their light is still traveling, still telling the story of a past that has already disappeared. For the first time, humanity understood that the universe has a memory, and that memory travels at a finite speed. It was one of the greatest discoveries in scientific history, but it created an even bigger mystery, because once scientists knew light had a speed, they wanted to know what light actually was. And that's where the story takes an unexpected turn, because the next discovery wouldn't just change our understanding of light, it would change our understanding of reality itself. Once scientists discovered that light had a speed, a new question emerged. What exactly was light? At first, nobody knew. It clearly wasn't ordinary matter. It could travel through empty space. It illuminated the world. It carried information across enormous distances. But what was it? A particle? A wave? Something else entirely? For centuries, the answer remained elusive. Then, in the 19th century, a physicist named James Clerk Maxwell changed everything. Maxwell achieved something extraordinary. At the time, electricity and magnetism were considered separate phenomena, different forces, different behaviors, different rules. Maxwell showed they were actually part of the same thing, a single unified framework. one of the greatest intellectual achievements in scientific history. But hidden inside his equations was an even bigger discovery, a prediction nobody expected. The equations suggested that electric and magnetic fields could travel through space as waves. And when Maxwell calculated the speed of those waves, he got a shocking result. The number matched the measured speed of light, exactly. Suddenly everything clicked into place. Light wasn't some mysterious substance. Light was an electromagnetic wave, a ripple moving through the universe. For physicists, it felt like the mystery had finally been solved. Case closed, or so they thought. Because Maxwell's breakthrough created a devastating new problem. Every wave ever discovered required a medium. Sound waves travel through air, ocean waves travel through water, vibrations travel through matter. A wave always moves through something. So what exactly was light moving through? Space appeared empty, completely empty. Yet Maxwell's equations clearly described a wave, and waves needed something to wave. The solution seemed obvious. Scientists proposed an invisible substance filling the entire universe. A medium so subtle that nobody could see it, touch it, or detect it directly. They called it the luminiferous ether. And for a while, the idea seemed perfect. The ether explained everything. Space wasn't really empty. It was filled with an invisible cosmic ocean. Light moved through that ocean just as sound moves through air. The theory was elegant, logical, beautiful, the kind of idea physicists love, which is often when trouble begins, because nature has a habit of ignoring beautiful ideas. The real test came when scientists tried to measure the ether directly, and the logic seemed straightforward. If Earth was moving through the ether, then Earth should experience something similar to a headwind. Imagine sticking your hand out of the window of a moving car. You feel air rushing past, not because the air is moving, because you're moving through it. The faster the car travels, the stronger the effect becomes. Scientists expected the same thing with Earth. As our planet orbited the Sun, it should be moving through the ether. That motion should create an ether wind, and that wind should slightly alter the measured speed of light. Not by much, but enough to detect. At least that was the expectation. Then two American physicists decided to test it, Albert Michelson and Edward Morley. What they built was one of the most precise scientific instruments ever created, an interferometer. The device was brilliant in its simplicity. A beam of light was split into two identical paths. Each beam traveled in a different direction. Then both beams were brought back together. If one beam moved even slightly faster than the other, the instrument would reveal it. The ether would finally be detected. Physicists were confident. The only question was how strong the effect would be. Then the measurements arrived, and physics received one of the greatest shocks in its history. There was no ether wind, none. The speed of light remained exactly the same. In every direction, every season, every measurement, nothing changed. The result wasn't merely surprising, it was impossible, according to everything physicists thought they knew. At first, scientists assumed there had to be a mistake, a faulty instrument, a hidden variable, an error in the calculations, anything, because the alternative was unthinkable. The alternative was that centuries of assumptions about space and time were wrong, so they repeated the experiment again and again and again. Different equipment, different locations, different conditions. The answer never changed. No ether, no explanation, no escape. The deeper scientists investigated, the worse the problem became, because this wasn't just a problem with light, it was a problem with reality itself. Imagine throwing a baseball from a moving train. To someone on the train, the ball travels at one speed. To someone standing beside the tracks, it travels faster. The velocity of the train gets added to the velocity of the ball. Simple. Everyone understood that. Velocities add together. It's one of the most basic rules in physics. Everyone agreed on it. Everyone, except light. You could move toward a beam of light, away from it, alongside it, and somehow the light always moved at exactly the same speed. Not approximately, exactly. The implications were terrifying, because if the speed of light never changes, then something much deeper must be changing instead. For nearly 20 years, some of the smartest scientists on Earth tried to save the old picture of reality. They failed. Every explanation solved one problem and created two more. Every promising solution eventually collapsed. The deeper they dug, the worse the contradiction became. It was as if the universe was refusing to follow the rules physicists believed it should follow. Then, in 1905, something unexpected happened. The breakthrough didn't come from a famous laboratory. It didn't come from a prestigious university. It didn't come from one of the world's leading physicists. It came from a patent office in Switzerland. The man responsible wasn't famous. He wasn't a professor. He wasn't even working in academia. His job was reviewing patent applications. Day after day, hour after hour, blueprints, technical drawings, mechanical inventions. Nothing that suggested he was about to change humanity's understanding of reality. His name was Albert Einstein. He was 26 years old. And unlike everyone else, Einstein wasn't trying to save the old picture of reality. He was willing to destroy it. While other physicists searched for flaws in the experiment, Einstein asked a dangerous question. What if the experiment isn't wrong? What if reality is? Pause. In that moment, Einstein did something extraordinary. He stopped asking how the universe worked and started asking what assumptions humans had been making about it. The answer would change everything. At first, Einstein's idea sounds almost harmless. Most people hearing it for the first time completely miss how radical it really is. Because Einstein wasn't saying that clocks sometimes run incorrectly. He wasn't saying measurements are difficult. He wasn't saying our instruments are imperfect. He was saying something far stranger. Imagine two people standing side by side. They synchronize their watches. They agree on the time. Then one of them leaves, travels at an enormous speed, and later returns. Common sense says both watches should still agree, maybe not perfectly, but close. Einstein said they wouldn't. Not because one clock malfunctioned, because time itself flowed differently for each person. Think about what that means. For thousands of years, humanity assumed the universe shared a single clock. One cosmic timeline, one universal now. Einstein destroyed that idea. According to relativity, there is no universal now, no master clock, no cosmic timestamp shared by everyone. Two observers can disagree about the amount of time between the same events, and neither observer is wrong. Read that again. Neither observer is wrong. Reality itself allows both perspectives to be true. The universe does not force everyone to agree on time. It only forces everyone to agree on one thing, the speed of light. Everything else is negotiable. Time, space, distance, duration. Reality bends all of them before allowing the speed of light to change. And once physicists realized that, they understood something extraordinary. The Michelson-Morley experiment wasn't revealing a problem with light. It was revealing a problem with our understanding of existence itself. The universe was far stranger than anyone had imagined, and Einstein had just opened the door. A theory can be beautiful, elegant, even convincing, but physics doesn't care about beautiful ideas. Physics cares about evidence. And if Einstein was right, the universe should be leaving clues, real clues. Not in equations, not in textbooks, in reality itself. As it turns out, it was. And those clues were falling from the sky, every second of every day. A theory can be beautiful, elegant, even convincing. But physics doesn't care about beautiful ideas. Physics cares about evidence. And if Einstein was right, the universe should be leaving clues, real clues, not in equations, not in textbooks, in reality itself. As it turns out, it was. And those clues were falling from the sky, every second of every day, long before humans built particle accelerators, long before anyone had heard of relativity. The universe was already running the experiment. High above Earth, particles called cosmic rays constantly slam into our atmosphere. They arrive from deep space carrying enormous amounts of energy. When they collide with atoms in the upper atmosphere, a chain reaction begins. New particles explode outward in every direction. One of those particles is called a muon. At first glance, a muon doesn't seem particularly important. It's small, unstable, and short-lived, very short-lived. A muon survives for just over 2/1,000,000th of a second before decaying. That's it. Then it's gone. Normally that wouldn't be interesting, except for one problem, a very big problem. Most muons are created roughly 10 kilometers above Earth's surface, and according to classical physics, they should never make it to the ground. The numbers simply don't work. Even traveling close to the speed of light, most muons should disappear long before reaching us. The math was clear, the prediction was clear, The case seemed closed. Then physicists started counting, and the numbers refused to cooperate. Again, and again, and again. Muons kept reaching Earth, millions of them, every second, passing through buildings, passing through mountains, passing through you, right now, at this very moment. Tiny visitors from the upper atmosphere are passing through your body. And according to classical physics, they shouldn't be here. For a while, it looked like a mystery. Then Einstein's theory entered the picture, and suddenly everything made sense. From our perspective, the muons are moving incredibly fast, so fast that time slows down for them. Their internal clocks tick more slowly, their brief lifespan stretches, they survive long enough to complete the journey. Mystery solved. Except it gets even stranger, because from the muon's perspective, something entirely different is happening. The muon doesn't see its own clock slowing down, instead it sees Earth rushing toward it. The atmosphere becomes thinner, the distance shrinks, the journey itself becomes shorter. Two completely different explanations, one identical result, and both match reality perfectly. That was the moment many physicists realized Einstein wasn't merely proposing an interesting theory. He had discovered something fundamental about the universe. Time is not absolute. Space is not absolute. Reality itself depends on who is observing it. And the faster you move, the stranger that reality becomes. Because if a tiny particle can experience time differently, what happens to a human being? What happens to a spacecraft? What happens when something gets even closer to the speed of light? The answer is where the story becomes truly unsettling, because the universe doesn't simply allow strange things to happen near the speed of light. It begins fighting back, harder and harder and harder, as if you're approaching a boundary you were never meant to cross. And the first warning sign arrives in the form of something every civilization understands: a price. Imagine you're building the fastest spacecraft in human history, not 10 times faster than today's rockets. Not 100 times faster, something far beyond anything humanity has ever created. A ship capable of accelerating continuously for years. You launch, the engines ignite, the stars begin to drift behind you. At first, everything behaves exactly as expected. More energy, more speed, simple. The relationship feels familiar. Push harder, go faster. That's how motion works, or at least that's how it works at everyday speeds. Then something strange begins to happen. The ship keeps consuming energy, enormous amounts of it, yet each additional burst of speed becomes smaller than the last. At first, the difference is barely noticeable. Then it becomes obvious. Then impossible to ignore. The closer you get to the speed of light, the worse it gets. It's like climbing a mountain that becomes steeper with every step. You keep moving upward, but the summit never seems any closer. No matter how hard you push, no matter how much energy you spend, the destination remains just out of reach. For years, physicists struggled to understand why. Then the mathematics revealed something astonishing. The speed of light isn't a wall, it's something even more frustrating. An asymptote, a limit that can be approached forever, but never reached. Imagine trying to touch the horizon. You can walk toward it your entire life. Every step brings you closer, yet somehow it always remains ahead. The speed of light behaves the same way. At 90% of light speed, things are strange. At 99%, they're stranger. At 99.9%, the situation becomes absurd. Each tiny increase in speed demands vastly more energy than the one before it. And then comes the realization that changed everything. To actually reach the speed of light, pause. You would need infinite energy. Pause. Not an enormous amount, not a civilization-spanning amount, not the output of 1,000,000 stars, infinite, a quantity that does not physically exist. The requirement is so extreme that the universe effectively says, no, not difficult, not unlikely, impossible, and suddenly the speed of light starts looking different. This isn't a challenge waiting to be solved, it's a boundary built into reality itself. Because if infinite energy is required, then no engine can ever be powerful enough, no fuel source can ever be large enough, no technological breakthrough can ever be clever enough. The barrier survives every future invention, every future civilization, every future dream, and that's what makes it so unsettling. Most limits in history eventually fell. The speed of sound fell, gravity fell, distance fell. This one doesn't seem interested in negotiation. The universe simply refuses the transaction. And that's when physicists began asking a disturbing question. What exactly is the universe protecting? Why build such an extreme barrier around one particular speed? Why demand infinite energy just to cross a single boundary? The answer becomes even stranger when you realize that energy isn't the only defense, it's just the first one. Because while the universe is demanding more energy, something else is happening, something far more bizarre. Time itself is beginning to unravel. The twins. At first, time dilation sounds like a strange scientific fact. Interesting, counterintuitive, maybe even fascinating, but still abstract. Then you realize what it actually means. Imagine you have a brother, not just a brother, a twin. The two of you were born on the same day. You grew up together, shared the same childhood, the same birthdays, the same memories. For your entire lives, time treated you exactly the same. Then one day, an opportunity appears, humanity's first mission to another star, and you're chosen to go. The spacecraft is unlike anything ever built, powerful enough to travel at nearly the speed of light. The mission will take years, at least from your perspective. Before departure, your brother walks with you to the launch site. You talk, you laugh, you make promises. You'll be back before he knows it. Then the countdown begins. 10, 9, 8. The engines ignite, and for the first time in your lives, the two of you begin traveling through time at different rates. At first, nothing feels unusual. Life aboard the spacecraft feels normal. You wake up, you eat, you work, you sleep, you celebrate birthdays, you complain about the food, you count the days. The mission becomes your life. Years pass, but not many. Eventually the journey ends, and you come home. As your ship descends through the atmosphere, excitement takes over. You're finally back. Back to Earth, back to your family, back to your brother. Then the hatch opens, and something feels wrong. The world looks different. The buildings are unfamiliar. The technology has changed. The people speak differently. At first, you assume you're imagining it. Then you see him, your brother. Only it doesn't feel like your brother anymore. The man standing in front of you is old, much older than you. His hair is grey, his face is lined with wrinkles, his hands tremble. You left as equals. Now he looks old enough to be your father, maybe even your grandfather. While only a few years passed for you, decades passed for him. An entire lifetime unfolded while you were away. He fell in love, built a family, raised children, maybe grandchildren. He celebrated birthdays, attended weddings, buried friends, experienced triumphs, experienced heartbreak, lived a life, and you missed all of it. Not because you traveled far, because you traveled fast. Your brother didn't travel through time. You did. Pause. And the universe considers that perfectly normal. That's the part most people never forget. Time dilation isn't really about clocks. It's about people. It's about two lives that begin together and slowly drift apart. Not through distance, through time itself. And the strangest part is that neither person notices anything unusual while it's happening. Your watch works normally, your heartbeat feels normal, your thoughts feel normal. From your perspective, nothing changed. Reality changed around you. And this isn't science fiction. It isn't speculation. It isn't a clever thought experiment. Nature does this for real. Every day, atomic clocks flown aboard aircraft measure it, GPS satellites correct for it, particles in accelerators experience it. The universe has tested Einstein's prediction millions of times, and every test reaches the same conclusion. Time is flexible, time is relative, time does not flow equally for everyone. And that realization leads to a disturbing question. If time slows more and more as you approach the speed of light, what happens at the limit itself? What happens when you finally reach the speed that reality seems so desperate to protect? Because according to Einstein's equations, that's where things become truly impossible. At the speed of light, time stops. Completely. Not slows down, not nearly stops, stops. For us, that idea sounds absurd, because every aspect of our existence depends on time. Every thought, every memory, every heartbeat, every chemical reaction inside your body. Everything requires time to move forward. Without time, nothing happens, no change, no motion, no life, no experience, nothing, which creates a bizarre paradox. How can anything with mass ever reach a state where time itself disappears? The answer is simple. It can't. Reality refuses to allow it, because reaching the speed of light would require an object to enter a state that seems incompatible with existence itself, a state where change becomes impossible, a state where time no longer flows, another barrier, another warning sign, another layer of protection. But physicists weren't finished, because hidden inside Einstein's equations was another disturbing consequence. One that most people never hear about. Imagine looking out the window of your spacecraft. Ahead of you lies a distant star, a destination many light years away. Normally that distance would seem enormous, but as your velocity increases, something strange happens. The distance begins to shrink, not from Earth's perspective, from yours. The faster you move, the shorter the journey becomes. The universe itself appears compressed. Space contracts. Stars seem closer. Distances seem smaller. Reality bends to preserve the same rule. The speed of light remains constant, always, no exceptions. And that's when a remarkable pattern begins to emerge. Every time you approach the limit, reality changes, time changes, space changes, energy requirements change, everything changes. Everything except one thing, the speed of light. It's as if the universe is willing to rewrite every other rule before allowing that boundary to break. And that raises an uncomfortable question. Why? Why is this one number so important? Why does reality seem willing to distort space and time themselves just to protect it? The answer becomes even stranger when quantum physics enters the story, because according to one extraordinary prediction, if you keep accelerating toward the speed of light, the vacuum of space itself begins to transform. The emptiness around you stops being empty. Darkness begins to glow. Heat begins to appear from nowhere. And the closer you get to the limit, the more the universe seems to fight back, as if reality has one final warning left to give. Because beyond the barriers of energy, and beyond the barriers of time, there may be something waiting in the vacuum itself. Something that turns empty space into fire. Most people think of empty space as exactly that, empty, a perfect vacuum. Nothing there, no air, no matter, no particles, just darkness stretching endlessly in every direction. For centuries that seemed reasonable. Then quantum mechanics arrived and destroyed the idea completely, because according to modern quantum theory, empty space is not empty, not even close. Beneath what appears to be perfect nothingness, reality is constantly in motion. Invisible particles flicker into existence, then disappear, again and again and again, across the entire universe. These events happen so quickly that we never notice them. The vacuum hides its activity remarkably well, but underneath the silence, something is always happening. Think of the ocean. From high above, the surface may look calm, smooth, peaceful. Yet beneath the surface, countless currents are moving in every direction. Quantum physicists discovered that empty space behaves in a surprisingly similar way. The vacuum isn't dead, it's restless, a sea of microscopic activity hidden beneath reality. Normally, these fluctuations balance each other out. The chaos averages to zero. Space appears empty, stable, quiet. But according to a remarkable prediction made in the 1970s, that changes when you accelerate. Imagine our spacecraft again, still pushing toward the speed of light, still fighting the energy barrier, still fighting time itself. Now the engines become even more powerful. The acceleration grows extreme. From the perspective of an outside observer, nothing unusual happens. Space remains dark, cold, silent. But inside the spacecraft, something extraordinary begins to occur. The darkness starts to glow, not metaphorically, literally. Particles begin appearing where empty space should be. Radiation emerges from the vacuum itself. Heat begins filling the cabin. At first, the effect is tiny, almost impossible to detect. But the harder the spacecraft accelerates, the stronger it becomes. The vacuum grows hotter and hotter and hotter. This prediction is known as the Unruh effect. And if it is correct, it implies something astonishing. Acceleration itself creates heat, not through friction, not through collisions, not through nearby stars, through empty space. The vacuum itself becomes a source of radiation. Imagine looking through the front window of the ship. At first you see darkness, then a faint glow, then a haze of radiation, then something that resembles a wall of fire stretching across the universe. Not because you're flying into something, because reality is reacting to your motion, as if the universe is sending a warning. slow down, stop, no further. Whether the Unruh effect has been directly observed remains one of the open questions in modern physics. The required accelerations are enormous, far beyond anything humanity can currently produce. But the mathematics behind the idea connects to another prediction physicists take very seriously, a prediction made by Stephen Hawking, Hawking radiation. The radiation expected to emerge from black holes, different phenomenon, same underlying principles, which means the idea cannot simply be dismissed. And if the prediction is correct, the picture becomes extraordinary. First, reality demands infinite energy. Then it slows time. Then it reshapes space. Then the vacuum itself begins to burn. One barrier might be a coincidence. Two barriers might be surprising. Four independent barriers, all pointing toward the same conclusion. That's something else entirely. It's almost as if every layer of physics is defending the same boundary, the same invisible line, the same forbidden speed. But despite all of that, none of these barriers explain the deepest mystery, because every obstacle we've encountered so far is physical. Energy is physical, time is physical, space is physical, even quantum radiation is physical. And throughout history, humanity has become remarkably good at overcoming physical problems. Which raises an obvious question. Suppose a future civilization solves all of them. Suppose it discovers unlimited energy. Suppose it learns to manipulate space-time itself. Suppose it finds a way around every physical barrier we've discussed. What happens then? That's where the story takes its darkest turn, because beyond every physical obstacle lies something far more dangerous, something far more fundamental. Not a barrier created by nature, a barrier created by logic itself. And once that barrier breaks, reality stops making sense. The most important discovery. Up to this point, every barrier we've encountered has been physical. The universe demands impossible amounts of energy. Time slows down, space contracts. The vacuum itself begins to fight back. Strange, fascinating, but ultimately physical. And throughout history, humanity has become remarkably good at solving physical problems, which raises an obvious question. What if a future civilization overcomes all of them? What if it discovers a limitless source of energy? What if it learns to manipulate space-time? What if it finds a way around every obstacle we've discussed? Would faster-than-light travel finally become possible? At first, the answer seems like it should be yes. Then physicists discovered something terrifying. The real barrier isn't physical, it's logical. And logic is much harder to negotiate with. Every event in your life follows the same rule. A cause happens first, then an effect follows. You strike a match. The flame appears. You press a key. A letter appears on the screen. You ask a question. Then you receive an answer. Simple, obvious, almost boring. Yet this rule is so fundamental that we rarely think about it. Cause, then effect. Always. The entire universe appears to run on that sequence. History depends on it, science depends on it, memory depends on it, your entire identity depends on it, because if causes don't come before effects, nothing has an explanation anymore. This is the moment most people misunderstand. Faster-than-light travel isn't dangerous because it breaks physics. It's dangerous because it breaks the idea of before. Pause. Read that again. Not matter, not energy, not technology, before. The concept itself. Imagine humanity invents instant communication. No delays, no waiting, no speed limit. A message can cross the galaxy instantly. At first, it sounds incredible. The greatest communication system ever created. Then relativity enters the story, and everything changes. Because instant is not the same for every observer. To someone moving differently through space, that same message may arrive before it was sent. Not quickly, not almost instantly, before. The effect arrives before the cause, the answer arrives before the question, the future arrives before the past, and suddenly the problem is no longer technological, it's existential. Imagine checking your phone tomorrow morning. A new message appears, only 6 words. Do not send the transmission. No explanation, no context, no sender, just those words. Later that day, you prepare to send an important message. Then you remember the warning, so you stop. You never send it, which creates a problem. If you never sent the transmission, who sent the warning? And if nobody sent the warning, why did you receive it? The message exists, but its origin doesn't. Information appeared from nowhere. A consequence created its own cause. A loop with no beginning, no creator, no explanation. And once loops like that become possible, reality starts breaking in ways that are difficult to describe. Because every explanation depends on an earlier explanation. Every event depends on a previous event. Every story depends on a beginning. Remove that structure, and the universe loses its ability to explain itself. Cause and effect become interchangeable. Questions create answers. Answers create questions. The future creates the past creates the future. Everything becomes trapped inside contradiction. And that's when physicists realize something extraordinary. The speed of light isn't protecting itself, it's protecting causality. The chain connecting every event in existence, every heartbeat, every memory, every star that has ever formed, every thought you have ever had. Everything depends on the distinction between before and after, and the speed of light enforces that distinction. Suddenly, every strange barrier we've encountered starts making sense. The infinite energy, the slowing clocks, the contracting distances, the burning vacuum, different mechanisms, same purpose. It's almost as if every layer of physics is defending the same boundary, the same invisible line, the same fundamental rule. The universe is not trying to stop us from reaching the stars. The universe is trying to prevent contradictions. It's protecting the story of reality itself. And once you see that, the speed of light stops looking like a speed limit. It starts looking like a firewall, a boundary separating a logical universe from one that cannot explain its own existence. Just when it seemed the universe had closed every possible door, physicists found a crack in the wall. And that crack leads to one of the strangest ideas ever proposed, a shortcut through space-time itself. At this point, the story should be over. The speed of light wins. Case closed. No shortcuts, no loopholes, no path to the stars. The universe has made its decision, or so it seems. Because just when it looked like reality had closed every possible door, physicists found a crack in the wall. A tiny one, but a crack nonetheless. And it emerged from Einstein's own equations. The very theory that seemed to make faster-than-light travel impossible. The key insight was surprisingly simple. The speed of light limits how fast you can move through space. But what about space itself? Does space obey the same rule? Surprisingly, the answer appears to be no. In fact, the universe has been demonstrating this for billions of years, right in front of us. The universe itself is expanding. Galaxies are moving away from one another, and some are receding so quickly that the distance between them grows faster than light. Not because the galaxies are breaking relativity, because space itself is stretching. And suddenly a fascinating possibility appears. What if the speed limit only applies to objects moving through space-time, but not to space-time itself? That idea changed everything. The wormhole. Imagine drawing two dots on a sheet of paper. One dot is Earth, the other is a distant star. The distance between them is enormous. Now fold the paper. The dots touch. Punch a hole through the fold, the journey becomes almost instantaneous. You didn't move faster, you changed the geometry. That is the basic idea behind a wormhole, a tunnel through space-time, a shortcut connecting regions of the universe that would otherwise be impossibly far apart. And here's the incredible part. Wormholes aren't science fiction inventions. They emerged naturally from Einstein's equations. The mathematics allows them. Reality is the problem. Because the moment a wormhole forms, the universe tries to destroy it. Immediately, gravity crushes it shut. The tunnel collapses. The shortcut disappears. To keep it open, physicists need something extraordinary, a substance unlike anything in ordinary experience. Negative energy, not less energy, negative energy. A form of energy that behaves in ways that seem almost impossible. Tiny hints of it appear in quantum mechanics, but only in microscopic amounts. Keeping open a wormhole large enough for a human being. That's an entirely different challenge. It's the difference between lifting a feather and lifting a mountain. And yet, the equations refuse to rule it out. The possibility remains. A tiny crack in the wall. Then things become even stranger, because wormholes create a familiar problem. The same problem that keeps returning throughout this story. Time. Imagine one end of a wormhole remains on Earth, the other travels aboard a spacecraft moving near the speed of light. Years pass. Time dilation takes effect. The two entrances age differently, and suddenly something impossible becomes possible. You enter one side and emerge before you entered. Not somewhere else, somewhere else. The wormhole becomes a time machine, and instantly all the old paradoxes return. The warnings, the contradictions, the collapse of causality, different mechanism, same danger. It's almost as if reality keeps steering us back toward the same conclusion. The warp drive. Then came an even more radical idea. One that sounded less like physics and more like science fiction. The warp drive. Most people know the concept from movies and television, but in 1994, physicist Miguel Alcubierre discovered something remarkable. The mathematics actually works, at least on paper. Imagine standing on a moving walkway at an airport. You're barely moving, yet the floor carries you forward. The Alcubierre drive uses a similar trick. Instead of accelerating a spacecraft through space, it moves space itself. Space in front of the ship contracts. Space behind the ship expands. The spacecraft sits inside a bubble. Locally, it never breaks the speed of light. Yet from the outside, the bubble can cross enormous distances at extraordinary speeds. For a moment, it looked like the ultimate loophole, a way around Einstein without violating Einstein, the perfect solution. Then, physicists started doing the math, and reality struck back. Again, the energy requirements were absurd. The engineering challenges were worse, and even if both problems could somehow be solved, new questions appeared. How do you steer the bubble? How do you stop it? What happens when it arrives? What happens to everything in front of it? Every answer created new mysteries. Every loophole revealed new obstacles. And once again, the universe seemed determined to defend the same boundary. That's what makes this story so fascinating, because every time physicists think they've found a way around the speed of light, they eventually collide with the same thing. Not energy, not technology, not engineering, causality. The deeper you dig, the more it appears that causality is the real rule, and the speed of light is simply the mechanism enforcing it. The big idea. At the beginning of this story, we asked a simple question. Why can't anything move faster than light? At first, it sounded like a problem of engineering, a problem of propulsion, a problem of technology. Build a better engine. Create a more powerful energy source. Eventually, the barrier falls. That's how progress usually works. But every step of this investigation pointed somewhere unexpected, because the deeper we looked, the less the speed of light behaved like a technological limitation, and the more it behaved like a fundamental rule, a rule woven into reality itself. Think about what we've discovered. The universe demands infinite energy. Time slows down. Space contracts. The vacuum begins to react, and every apparent loophole eventually crashes into the same obstacle. Causality, again and again and again. At some point, the pattern becomes impossible to ignore. The speed of light isn't protecting itself. It's protecting something built on top of it. Imagine a skyscraper. Most people never think about its foundation. They admire the glass, the height, the architecture, the view. The foundation remains invisible. Yet remove it, and everything above collapses. Not because the foundation is special, because the entire structure depends on it. Reality may work the same way. For centuries, we assumed light was the important part of the story. Maybe it never was. Maybe light is simply revealing something deeper, a hidden rule governing the universe, a rule that determines how information moves, how events connect, how causes create effects, a rule that allows reality to remain consistent. Some physicists believe this idea points towards something even stranger, the possibility that space-time itself is not fundamental, that space and time may emerge from something deeper, something beneath the reality we experience. Different theories propose different answers. Quantum information, quantum geometry, networks of microscopic connections. The details remain uncertain, but many of these ideas share a fascinating implication. Reality may be less like a stage and more like a process. Think about a computer. Every processor has a maximum speed. Not because engineers enjoy limitations, because the system requires one. Information can only move so quickly through the hardware. Push beyond that limit, and the system stops functioning correctly. Now imagine reality operates in a similar way. Not literally. The universe is not necessarily a computer, but the analogy is useful. The speed of light may represent the maximum rate at which information can move through the structure of existence itself. The the maximum rate at which reality can remain internally consistent. And suddenly everything begins to fit together. Time dilation, length contraction, the energy barrier, the paradoxes, the endless defense of causality. They're not separate mysteries, they're different consequences of the same underlying rule. Reality has a maximum information speed, everything else follows, which means we may have been asking the wrong question all along. The question was never, why can't we move faster than light? The real question is, what would happen if reality allowed us to? And after everything we've seen, the answer appears surprisingly clear. Reality would stop making sense. The distinction between before and after would disappear. Cause and effect would collapse. The universe would lose the structure that allows it to explain itself. The story would break. And perhaps that's the most surprising discovery of all, because humanity has always dreamed of breaking limits, crossing boundaries, reaching the unreachable. But not every limit is a prison. Some limits are foundations. Remove a prison wall, and freedom appears. Remove a load-bearing wall, and everything falls. The speed of light may be one of those walls, not a cage surrounding reality, a framework supporting it. The message from tomorrow. At the beginning of this story, we imagined receiving a message from the future, a warning that arrived before it was sent. At the time, it sounded like a miracle, a breakthrough, proof that humanity had finally conquered the universe. Now we understand why that message never arrives. Not because the stars are too far away, not because our technology is too primitive, but because reality depends on it. The distinction between before and after, cause and effect, question and answer. Everything we call existence depends on those relationships, and the speed of light protects them. For centuries we viewed it as a barrier, a limitation, a wall standing between humanity and the stars. But maybe we had it backwards. Maybe the speed of light isn't the wall. Maybe it's the foundation beneath everything, the thing we spent centuries trying to overcome. Maybe the very thing making our existence possible, and perhaps that's the strangest discovery of all. Call to action. So here's the question. If humanity discovered a way to bypass the speed of light tomorrow, would you take the journey, even if it meant risking the rules that make reality possible? Let me know in the comments. And if you enjoyed this exploration into one of the deepest mysteries in physics, subscribe for more. Because some of the most extraordinary secrets in the universe aren't hidden in distant galaxies. They're hidden inside the rules we've taken for granted our entire lives. And those rules may be far stranger than we ever imagined.